Okay, thank you. So yesterday I explained how Haldane actually reached his famous conjecture for the first time based on the Nondegeneracy theory or bosonization. And yeah, it was kind of heuristic, but today I want to examine his approach a bit more carefully. Then we can see how you can generalize his observation to more general 1D quantum many-body systems. Then it's kind of easy to guess generalization for higher dimensions. And then I will explain how alternatively we can see the same conclusion without using bosonization or Tomonaga-Lattice theory. Okay, so to recap, so he basically tried to so-called bosonize, that is to obtain the low energy effective field theory for quantum spin chains. Then the low energy effective field theory of this Hamiltonian is given by free boson field theory, but plus some perturbations. And if all the perturbations appearing here are irrelevant in the renormalization group sense, then if you go to very low energy limit, then eventually you can forget about this perturbation and you are left with just free boson field theory. That's Tomonaga-Lattice. But in general, we have various perturbations. And if one of them are relevant perturbation, then the relevant perturbation grows. So the system is driven into something else. Usually it's gapped phase. So that's the story. And what he found out was that even for this simple Hamiltonian, the possible perturbations appearing here depend on the spin quantum number. So if spin is integer, so this perturbation includes cosine of 2 phi, cosine of 4 phi, and so on. But if spin quantum number is half odd integer, 1/2, 3/2, and so on, then this most leading operator is somehow forbidden. So, this is a listing of these possible perturbations. So this leads to the difference between the property of this simple spin chain Hamiltonian depending on spin quantum number was integer or half odd integer. So I explained yesterday how you can see this difference, but it's a bit complicated, and it's kind of heuristic. But now I want to generalize this observation to more general cases. Then this kind of difference can be more naturally understood. That is actually, so as I explained yesterday, to derive this effective theory, you first, well, there are various different approaches, but one approach I explained yesterday was to map this spin chain to a system of many particles, many bosons. Then you obtain low energy effective theory for the many interacting boson system. Then you discuss this perturbation. So actually it's more maybe convenient and transparent to think about this system in terms of many particles, interacting many particles, instead of starting from this spin model. Of course, they are equivalent. And also, in analyzing the possible perturbations, yeah, we can also use general principle. That is, so this and so in more general setting, and also using more general principle. The general principle is that okay, suppose you start from some model like interacting many particles in one dimension. Then suppose you obtain this effective field theory. Okay, that's a framework I'm using right now. Of course, in some cases, this description may be completely invalid, maybe. So in that case, I will discuss later how to understand this kind of question without using this field theory. But for the moment, let me assume that this framework at least makes sense. So this free boson field theory plus some perturbation. Then question is, what kind of perturbations you can possibly have? And the general answer or general principle is that you should get any perturbation in principle if it's not forbidden by symmetry. So, yeah.
So in this half-arbitrator case, is it that for the symmetry?
Yeah.
Yeah.
That's what I'm going to say. Yes. So this is a general principle, and actually, yesterday there was some questions, so I mentioned another possibility is that this is for generic case. So maybe I should say generically. By generically, I mean if you introduce some parameter in the Hamiltonian and then change this parameter continuously, then maybe at some point, coefficient of some operator might vanish. So that is possible. That's something called fine-tuning in field theory or something. So if you fine-tune the parameter, you can make some of the coefficient vanish. So for example, for integer spin chain, generically you have cosine 2 phi, which is most likely relevant. But if you introduce some parameter in the Hamiltonian and change this parameter, then the coefficient of this operator will change in general continuously. So you can expect at some point the coefficient vanishes. Then in this framework, you are in similar situation like this. That is possible, but that requires fine-tuning. So that's, by that I mean generic. But this spin chain is not fine-tuned. Well, you can change value of delta, but otherwise. So this is kind of natural Hamiltonian, then we should expect generic situation, then you should expect this. So from this principle, it's important to understand what kind of symmetry you have and how those symmetries act on the effective field theory that is Tomonaga anti-delegate. So what are the symmetries? So if you start from this kind of Hamiltonian, you can see explicit symmetry that is for this XXZ spin chain, you have U1 symmetry, that's rotation about z-axis. You rotate every spin by same angle about z-axis. That's U1 symmetry. This is rotation. And if you map this spin chain to many particles, this rotation about z-axis becomes addition of phase. Used theta, let's say phi to times E alpha, and phi dagger goes to phi dagger. So rotation about z-axis in spin chain language becomes this U1 symmetry in many particle physics context. And this is nothing but constant change of quantum mechanical phase of wave function of this many particle system. So, and if you remember my bosonized expression, this annihilation operator is like a square root of density times e to I theta. And this was some boson field. And if you compare these two, adding extra phase factor to this psi is equivalent to constant shift of this theta. So this is a U1 symmetry, and this theta is periodic variable, the angular variable, but you can add some constant, and this corresponds to the U1 symmetry. So actually, I didn't discuss yesterday, but there are physical operators which corresponds to exponential of I theta. For example, this is physical operator, and roughly speaking, leading term is given by e to I theta because there is some constant part of rho. So cosine of theta, cosine of 2 theta, and so on. Also, you can have sine, and these are physical operators. But all those series, each operator is not invariant under this U1 symmetry. So as long as your Hamiltonian is invariant under this U1 symmetry, then these operators are forbidden. Or Lagrangian. So actually, yesterday I skipped this part, but in principle, you should also worry about these kind of perturbations because these can be relevant. And in fact, for large part of the phase diagram, these operators, especially this one, is relevant. The scaling dimension, for example, when this operator becomes relevant, it's a usual BKT transition. So at that point, this corresponds to Sx, Sy. So Sx, Sx correlation function has critical exponent 1/4. That's what I explained on Monday. So correlation exponent 1/4 means that this operator has scaling dimension 1/8, which is much less than 2. So this can be relevant perturbation. But as long as your starting point, microscopic Hamiltonian, is U1 symmetric, then this kind of term cannot appear here. So that's important part of the story I omitted. But so this is a good example how this general principle works. And in fact, I don't have much time to discuss this, but once you break the symmetry, then you can have this kind of perturbation, and then it can open the gap. That's another interesting story, which I can tell. But okay. So this is one side, but still we need to worry about this cosine of 2 phi, 4 phi, and so on. Then what I can say is that if this U1 is the only symmetry, then generically all these perturbations should appear. So there must be some symmetry which forbid this for half-odd integer spin chain. And
yeah, if you just look at it from another without any perturbation, then there's a sort of then there are two U1s in a sense. Maybe you are going to talk about.
Right. Exactly.
I was just wondering if there's so here it's one U1 is the physical symmetry, but then there is this other.
Yeah, that's what I'm going to discuss. Yes, exactly. Yeah. So that's what I'm going to discuss. That is, there must be another symmetry, and okay, I erase. But if you look at the original Hamiltonian, there is another important symmetry. That's a translation symmetry. That is, you shift S alpha j to, let's say, S alpha of j plus 1. So just shift every spin to next side. That's a lattice translation symmetry. And this is exact symmetry of the original microscopic Hamiltonian. Then the question in the field theory context is what is the representation of this symmetry in terms of these field variables. And for that, actually, you can go back to the, so it has nothing to do directly with theta field, but this one is connected to the phi field. And actually, once you realize it's kind of simple, because my phi field was introduced so first I introduced a so-called labeling field to represent the position of each particle. Then I subtracted the linear part, and then a phi field is to represent fluctuation around the average. So the definition I gave is yeah. Actually, I wish they didn't put this factor too, because it just makes less transparent, but this is a convention. Okay. So this was the kind of definition of phi in phenomenological bosonization scheme. And lattice translation means that you shift the coordinate x by the lattice constant. So if you, so this A is lattice constant. That's the spacing between the neighboring sites. So if you do this, you get some extra constant. So that means that this phi field and precisely speaking, this x is replaced by x plus a. But then you get this extra constant. So this and this are slightly different, but in the low energy effective field theory, we assume that the phi becomes some smooth or continuous field. So in the continuum limit, not A. Continuum limit means A to 0. Yeah, of course, if you are interested in spin chain model, you might say, okay, lattice constant should be 1. So what does it mean? Even if lattice constant is 1, the continuum limit means that you are interested in large scale phenomena at a length scale much, much larger than lattice scale. So that can be conveniently expressed by this continuum limit. Putting some lattice constant as a parameter, then take this limit, then you are automatically looking at the phenomena at large length scale, much, much bigger than lattice scale. So if you do this, then basically this and this indistinguishable. So you can just say 2 phi goes to, well, maybe phi goes to phi minus pi times goes away. Okay, you might say, okay, this A in continuum limit should be 0. But if you take continuum limit, if you start from lattice model, typically this rho 0 is number of particles per site or unit cell. Sorry, this is a particle density, so particle number per unit length. So this also diverge. So this product is order 1 quantity, which is fixed by lattice. So this rho 0 times A, this is order 1 quantity even in the continuum limit, which we sometimes often write as nu. And this parameter means number of particles. So if you start from spin chain, number of magnons per site, or more generally, number of particles per unit cell of this discrete lattice transition symmetry. So if you fix the microscopic model Hamiltonian like a spin chain, then this nu is basically fixed. And even if you take continuous limit, this is some constant quantity. And then in the field theory, this Tomonaga-Tinjarigi theory, this lattice, discrete lattice transition symmetry, you just translate by one side. So x goes to x plus a, but if a goes to 0, then x and x plus a, okay, almost indistinguishable, but still this field phi should be shifted by constant. So this constant shift of phi is this constant phi shift of phi is basically representation of the discrete lattice transition symmetry in this bosonized field theory, Tomonaga-Tinjarigi theory. And so in this view, the difference between the half odd integer spin chain and the integer spin chain becomes, in some sense, more understandable because, yeah, yesterday I discussed, but integer spin chain case. This rho zero, for in general, spin chain, if we start from Heisenberg antagonist chain, I discussed that this rho zero is given by S spin quantum number divided by A. So, which means that this nu is rho zero times A, which is nothing but the spin quantum number. So, in more general context, this spin quantum number in spin chain gives you this parameter nu, which is often called filling factor in condensed matter. Then the distinction between integer spin chain and half-odd integer spin chain is just that this filling factor is integer or half-odd integer. And now, let's look at the potentially relevant operator. Cosine 2 phi. And actually, in the context of Berezhinsky-Kostaritz-Saures transition picture, this is the creation annihilation operator for fundamental vortex. And so this may be relevant or irrelevant depending on the Rattinger parameter K, but this is potentially relevant operator. And now it's easy to see whether this operator is permitted in the presence of lattice translation symmetry. So under lattice translation, phi goes to phi minus pi nu. So cosine of 2 phi goes to cosine of 2 phi minus 2 pi nu. So if nu is integer, then this is invariant. So this is cosine equal to cosine 2 phi if nu is integer. But if nu is half odd integer, then you shift the argument of cosine by pi, then you flip the sign. So, yeah.
There is a difference between even integer and odd integer.
In this simple argument, no.
Why is cosine phi term not allowed?
Oh, cosine phi. Okay, that's kind of confusion introduced by this spurious factor too. So yeah, so in this argument, cosine phi seems to be permitted, but cosine phi usually doesn't appear due to compactification of variable phi.
Also in this language, it's probably not a local operator.
Right, yeah. So yeah, that's another subtle, but I kind of skipped. So yeah, basically 2 phi is another angular variable. So 2 pi shift, so pi shift of phi, that is 2 pi shift of 2 phi corresponds to shifting, re-leveling of each particle. So it's kind of, so this compactification was imposed by different requirement. Yeah, so it's a bit complicated, but we usually don't consider cosine phi because of other reasons. So yeah. So that's why for half odd integer spin chain, so this is not invariant. So this is forbidden by symmetry to appear in effective Lagrangian or Hamiltonian, and that's basically why Haldane didn't find this term for half odd integer spin chain. Although in his original paper he did find this by some explicit calculation, but in retrospect, there is a symmetry principle that's forbid. And once you understand this symmetry principle, you know, even if you add some different term in the Hamiltonian, as long as you don't change the symmetry, you cannot have this term. And so this is subset of the other U1 you mentioned, but only discrete side, yeah.
But the Tomonaga thing has a full translation.
Yeah, so once, okay, so the lattice model has only discrete lattice translation symmetry, which gives you, okay, I will discuss later, but if nu is some rational number p over q, then you have u1, which corresponds to theta rotation, times zq, discrete zq, and q is determined by the denominator of this fraction. So u1 times zq symmetry. But if all the perturbations turned out to be irrelevant, then in the infrared fixed point, you get rid of all those perturbations, so you have enhanced symmetry that is U1 cross U1.
Yeah, so I was wondering whether there's any system in which the other U1 remains is broken, but this U1 remains unbroken. So that instead of cosine phi perturbations, you have so some kind of dual.
We can create by some adding translation symmetry breaking term. For example, one example is okay, maybe I can discuss later, but you can add so-called staggered field that is magnetic pointing to, let's say, up on this side, and the next side magnetic field is pointing down, up, down, up, down. So if you apply this kind of staggered field, it gives a cosine theta type perturbation. So the low energy physics is described by Sine-Gordon type field theory with cosine theta perturbation. And yeah.
But is there something that would then prevent these cosine 2 phi perturbations?
Oh, okay.
There's that emergent U1, the other U1 is somehow unbroken, but the other U1 is broken to ZQ or something.
Yeah, so well, so I'm going to discuss if you change this nu, if make nu to very fractional number, then this ZQ with Q is very large, so it's almost like a U1. And then the other U1 of theta rotation, you can explicitly break by adding some term like a staggered field or a period for magnetic field or something like that. And yeah, but probably I'm not going to discuss today, but so the free boson field theory without these perturbations, Tomonaga-Rattinger-Likit, which is just free boson field theory in field theory terminology. But if you have just one cosine theta or cosine phi type perturbation, then the field theory consists of free boson kinetic term plus this cosine theta type perturbation is called Sine-Gordon field theory, which is integrable in 1 plus 1D. And a lot of things have been known. And actually, in some experimental system, you can realize this Sine-Gordon field theory with perturbation, and you can make a precise comparison between exact solution of Sine-Gordon field theory with numerical and also experimental result. That's a spontaneous breaking. Yeah. That spontaneous breaking is that's what I'm going to discuss now. But yeah.
If I am on-site SZ,
on-site.
to the Hamiltonian, on-site SZ.
SZ, okay.
That's good. That commutes with both translation and.
You mean just on one side?
Some over SZ.
Some over SZ. Okay, so that is Z. SZ doesn't break U1. And,
yes. So I can in principle add that.
Oh, yeah. Okay.
What should gap out?
You mean applying very strong magnetic field?
Okay,
you mean you start from Heisenberg chain and add small magnetic field in Z direction? That just change this nu little bit, and you don't gap out until saturation. Maybe you are thinking about different model than I do. Oh, SZ. Yeah, actually, it's related to this stuff, but SZ Bose-Einstein expression, okay, maybe it depends on convention, but SZ of J is written as this derivative term plus cosine of 2 phi or sine 2 phi depending on convention, but here you have -1 to J.
On the left hand side, that's invalid due to translation. There's some over on
This?
Yeah,
Yeah.
Sum over that.
Yeah.
But on the right hand side, by this thing that you showed there, it's not perturbation.
Yeah, so that's why, yeah. So if you sum over the entire system, this cancel out. Yeah, that's basically what, well, yeah. So I mean, yeah. So if you apply just magnetic field on single side, then you do have this one, but it's a local perturbation. If you take this sum, then in the continuum limit, this cancel out. That's what I mean. Okay. So in this way, we can rederive Haldane's observation just from general principle without much actual computation. And then related to Subro's question, so for half-odd integer spin case, we can rule out this perturbation due to this symmetry, but higher order terms can present like a cosine 4 phi. And it can be relevant depending on Latinger parameter k. The higher order terms tend to be less relevant compared to this one, but still depending on Latinger parameter, it can be relevant. So if nu is half odd integer, then cosine of 2 phi is forbidden. But cosine of 4 phi, so this is invariant under transition symmetry, as you can easily see. So if you make it 4 phi, then this becomes 4 pi nu, and the 4 pi times odd, half odd integer is 2 pi times odd integer, so it's invariant. So this is allowed. And this still can be relevant depending on Latinger parameter. Relevant. Depending on. So whether the system opens a gap or not depend on Latinger parameter k. So you need to determine the Latinger parameter k from exact solution or a numerical calculation or something in order to say final words on whether there's a gap or not, even if you accept this framework. So the answer is it depends, but we can still make some general statement without knowing value of Latinger parameter k about possible behavior of this system, just by knowing the filling factor nu. That's what I'm going to discuss. Yeah, well, yeah, so once you know the value of Latinger parameter k, then cosine 2 phi and the cosine theta has the same power of exponent. Yeah, that can be seen, yes. Yeah, actually, that's required because Sx and Sy corresponds to cosine theta and sine theta, and Sz corresponds to cosine 2 phi, and they must have the same correlation exponent because of the SU2 symmetry. Then Sz is represented by cosine 2 phi, then dimer operator is represented by sine 2 phi, and they must have the same exponent. So
Is there a way to understand this extra log for the position?
well, yeah, that comes from the marginally irrelevant perturbation. So you need to solve RG equation. So if you are at pure free boson fixed point, Latinger, then there is no log correction. But there are perturbation which is marginally irrelevant, but marginal, so it decays very slowly, so it affects this correlation function. So it's a bit more complicated. Okay, so the fate of the half-odd integer spin chain or the many particle system with half-odd integer filling, there are two possibilities depending on this value of k. So this cosine 4 phi, which is permitted. And if this is irrelevant, then in the low energy limit, this goes to 0. So we can forget about, and the low energy limit, large distance limit is described by free boson. That's we say Tomonaga-Tinja-Rigid. Then gapless. But depending on the Latinger parameter, this could be relevant. You need to find appropriate value of Latinger parameter, but it can be relevant. So in this case, we expect, okay, this part is not mathematically rigorous, but generally, if we add some relevant perturbation to the critical fixed point, then we expect gap. So at this point, the general statement seems like the system must be either gapless or gapped. That sounds like a trivial statement, and it is. But actually, this gapped phase must have some specific feature that we can see. The reason is, okay, so if relevant, you have a gap, but this gapped phase can be understood as the field theory with this cosine 4 phi interaction and a very large coefficient of this cosine 4 phi term, because this is relevant. So the question is, this is what kind of phase? And so this is phi, and so maybe I should first say so this gapped phase should be a gapped or massive field theory with very large interaction cosine 4 phi. Then, so adding cosine 4 phi to the Lagrangian or Hamiltonian is like this is a potential term for phi field. By which I mean you can plot phi versus cosine 4 phi. Then, of course, this cosine is a periodic function. I'm shifting, and it's periodic function. But okay, that part I didn't discuss very carefully. But as I mentioned a few times, this phi is like a so-called compact variable. If you shift phi by some amount, you basically get back to the original state, at least in the bulk. And the period of phi is basically pi because of the funny factor 2 used in the definition. So, so phi is 0, and this is phi equals to pi. And this between 0 and pi is 1 period, which means that phi can identify by phi plus pi. So this is something in string theory context called compactification. So phi is compactified like this. But this potential has a smaller period because of this factor 4. So cosine 2 phi has just 1 period in this range, but cosine 4 phi has 2 periods. So there are 2 minima, and this gapped phase caused by this potential can be understood as phi is basically localized in potential minimum, because this potential becomes very, very steep, then phi can only be here and maybe oscillate around this potential minimum. That gives you massive excitation, and the mass is given by this curvature. But the ground state is basically represented by phi trapped in this minimum of this cosine potential. So this is ground state. But then from this figure, it's obvious that if this is a ground state, this must be also ground state. So there must be 2 degenerate ground states, because cosine 4 phi has a shorter period. So, so from this, so this is a kind of inevitable consequence in the gapped phase when the filling factor is half odd integer. So if filling factor was half odd integer, this is permitted, and if this is irrelevant, you end up with gapless tangential. But if this is relevant perturbation, then you have a gap. But there is actually a constraint on the possible gapped phase, because if this cosine 4 phi operator opens up the gap in the system, then the ground state must be doubly degenerate. So this phase must have with twofold degenerate. Ground states. So the simplest case of gapped phase is like just having unique ground state, but this analysis suggests that if you start from half odd integer filling, then you cannot have a gap with unique ground state, that apparent constraint. So the gapped with unique ground state. So this sounds like a general possibility, but once we assume this and the U1 symmetry and the translation invariance, then this possibility is actually excluded. Yes?
On-site SZ term being very large is included.
Pardon?
On-site SZ term being very large.
Yeah. Yeah.
That's consistent with both U1 and term.
Yes, but in that case, actually, you are changing nu. Because nu is particle density, so if you apply magnetic field as the uniform magnetic field, you change the magnetization. And let's say for spin 1/2 case, if you go to limit of very strong magnetic field, all the spins point up. So the magnetization is 1/2, which corresponds to nu equals 1. Oh, that's in case of regular spin chain, there is kind of particle hole symmetry. Because, yeah.
I guess there's a very clear symmetry with this projected field. S equal to minus S integrated with
Mm-hmm. Yeah, time reversal symmetry you can also use. But once you apply magnetic field, you break time reversal. So there is no reason to fix nu to 0. Sorry, 1/2. So okay, so for practical application in general, in the absence of time reversal or particle hole symmetry, so the determination of this nu in the ground state is already non-trivial problem. Maybe you need to do some numerics or something for given model. Yeah. Yeah. Well, it's.
I would say that's the most important.
Mm-hmm. But what I'm going to discuss, once you fix nu, the rest of argument doesn't depend on time reversal. But of course, that's important symmetry, and basically that time reversal or particle hole symmetry is what fixes magnetization to 0 in the ground state of the original spin chain problem in the absence of magnetic field. Then we know the rest.
Again, this goes back to your work.
Mm-hmm.
I mean, some of these arguments would also go through on a magnetization plateau.
Yeah.
Where we don't have the angle.
Yeah. Of course, the argument I made here does not use, but our discussion about it was about how do we know the value of nu. So in general, it's not trivial, but in the presence of time reversal or particle symmetry, sometimes we can fix nu.
This twofold degenerate downstream argument is based on the fact that the most is determined by this cost factor, potential. But you also have this kinetic energy. Right? So when this cost item is not large, does this twofold degenerate downstream argument be there?
Okay, so you are worrying about the possible tunneling between these two. Okay, so the expectation is, so you are worrying about the possibility that you have a gap, but somehow these two ground state mix together and open the gap. Okay, so in this picture, it's actually, I guess, in principle possible, but okay, so this argument is not rigorous. First, we need to assume this Tomonara Lattinger-Likit framework, that the free boson plus some perturbation. But here, I'm arguing that, okay, so what happens if this cosine 4phi is relevant, grows to infinity? That's actually outside the validity of field theory approach. So you might worry about this final conclusion. That's legitimate concern. But what I'm going to introduce later is that there can be more rigorous kind of argument without relying on any field theory approach, which basically lead to the same conclusion. So in a sense, this is kind of conjecture you can make from field theory, which is certainly not rigorous. There are, can be many possible loopholes in this argument, but eventually we can confirm this by different arguments. So yeah, that's, at this point, I'm just making some partly hand-waving argument to find out this conjecture. So also maybe it's useful to give a few example of this. So we know various examples of a new half-odd integer system that is half integer spin chain, like a spin 1 half chain at zero magnetic field. For XXZ model, for small anisotropy, we have gapless Lattice-Jariquet. So examples. So let's say spin 1 half XXZ chain. So nearest neighbor interaction. And yeah, I discussed the ground state phase diagram of this model, which also motivated Haldane to study integer spin case. But for spin 1 half case, this has been exactly solved. And so this delta, this is -1, +1. And as I indicated, this region, in this region, the cosine 4 phi turned out to be irrelevant, and the system is eventually renormalized to Tomoda Lattice-Jariquet, so it's gapless. So this region is gapless. Lattice-Jariquet, which you can confirm from exact solution. But if you change delta, so above delta equals 1, actually cosine 4 phi becomes relevant. Then you open the gap. So in field theory language, in this region, cosine 4 phi exists but irrelevant. Up to this value, but beyond +1 becomes relevant and open a gap. But in this region, we know the nature of the ground state, which is known to be Nail state. And the nature of the ground state, you can understand easily by considering the extreme limit of delta goes to infinity. So if you send delta to infinity, then you are only left with this SGSE term. You can basically ignore the other terms. And if you just have this term, then ground state is pretty simple. One spin is pointing up, and the next spin is pointing down. Up, down, up, down, down, down. That's nothing but a Nail state, like up, down, up, down, up, down. But because of the translation symmetry, there are two different Nail states. You can have up, down, up, down, up, down, or down, up, down, up, down, up, and so on. So there are two ground states for delta infinity, and they have the same energy. And so this is a symmetry breaking, spontaneous symmetry breaking state. And there are twofold ground state degeneracy because of these two states. So this is twofold. And which is consistent with this statement. And also, you can consider so-called J1, J2 chain. So well, for this, we can also consider XXG version, but for simplicity, let's just consider Heisenberg model. That is, we have a coupling J1, S dot S, the Heisenberg coupling between these two, and this J1, J1, J1. But we also introduce next nearest neighbor coupling, this J2, also Heisenberg type, S dot S. And yeah, for every next nearest neighbors, we put J2 S dot S and then sum over this. And this model still has U1 symmetry, actually SU2 symmetry, but I don't have to use, it has SU2 symmetry, but of course, as a subgroup of SU2, you have U1. And then this model is still translation invariant, so it satisfies this requirement. And in this case, we can do the same, but the phase diagram of this model is known. And this is J2 over J1. And if J2 is 0, then if you remove this next nearest neighbor coupling, then only with J1, this is equivalent to Heisenberg chain, anti-ferromagnetic Heisenberg chain, which agrees with delta equals to 1 point of this phase diagram, which is still gapless Tomola-Rattinger-Likit. And if you crank up J2, for small J2, the ground state is essentially similar. So up to certain point, gapless Tomola-Rattinger-Likit. But there is some critical point, the value of which we don't know exactly, but numerically we know pretty accurately, like 0.2411. And above this point, you have gapped. And then what is the nature of this gapped phase? So actually, this gapped phase corresponds to spontaneously dimerized phase. Which can be pictorialized like putting singlet dimers like this. So these neighboring spins form singlet, and these neighboring spins form singlet, and this form singlet. You can pictorize like this. But because the original model is translation invariant, if this is a ground state, then there must be another ground state, like this. So again, this has a twofold ground state degeneracy. So in these simple examples, we can actually study actual phase diagram, and they are always consistent with expectation or conjecture you can make from the general symmetry principle. And so once you understand this, actually this kind of conjecture you can naturally expect even if you don't use any Tomola-Rattinger-Likit field theory renormalization group, because you have some lattice model, and particles are moving around, interacting with each other. And if nu is integer, then each unit cell can have integer number of particles. So you can easily imagine some stable state, which corresponds to ground state. But if nu is not integer, then you cannot easily draw some stable state. If some side has particle, but some other side is empty, then you expect this particle should be able to move to empty side. And if they don't move, you are somehow making pattern like empty state, occupied side, and the empty side and occupied side, which corresponds to this naive state. So yeah, by some kind of hand waving, even without relying on field theory, you can expect this kind of distinction. And yeah, I want to show that actually this expectation can be proved more rigorously without using field theory. But before that, I should mention that here I discussed just a case of integer nu and the half-odd integer nu, but the nu is the number of particles per unit cell, so in principle it can be changed continuously. So what about other values of nu? So if nu is rational, like a p over q, and p and q are co-primes, then cosine 2 phi is forbidden by the same argument, and the cosine 4 phi is also forbidden by the same argument. So you can eliminate many operators of this kind. And the first operator, which has the smallest scaling dimension, which is still permitted under this symmetry. So then this phi goes to phi minus pi p over q. And the first operator, which is permitted by symmetry, is 2 times q times phi. So usually this has, if q is large, then that's depending on Rattinger parameter. But if you fix the Rattinger parameter, then for large value of q, the scaling dimension of this guy is large, like a kq squared. So q is large, then scaling dimension is large. But still, if you can make Rattinger parameter pretty small, then you can make this relevant in principle. And but if this is relevant, because this operator has q independent potential minimum per one period of phi, which means that the system would be gapped, but the ground state must have q-fold degeneracy. Well, yeah, so as we discussed, for example, for spin chain, you can apply uniform magnetic field in z direction. Then because SZ component was related to, so one way of looking at the spin system is to identify this SZ equals to minus S state as a vacuum. And when you increase SZ from minus S, each time you put one particle. So the expectation value of SZ is related to the expectation value of the number of particles. So if you apply magnetic field, you can change the average magnetization, which is expectation value of SZ. Then that corresponds to changing the filling factor. So actually by, one thing we discussed long time ago was that even starting from half odd integer spin chain, at zero magnetic field, it's basically like a half odd filling factor, like a 1/2. But if you apply magnetic field, you can change nu. So at some point, you can make nu to be integer. Then it behaves then like an integer spin chain. So even if you don't change the translation symmetry, just by applying magnetic field, you can change nu continuously. And when nu hits integer, then you can open a gap. Yeah.
Is there, for example, a transition to a name from that?
Yeah. So, well, right. So, let's see. Yeah, I think you can just introduce both delta and J1, J2. And then, you can find some critical lines separating these two. And I think if I remember correctly, the critical transition between these two is again just a tonal Lattice. So it corresponds to some fine tuning, removing the relevant operator. So that's, actually it's kind of interesting from very general context because this Néel phase and spontaneous dimer phase are both just examples of spontaneous symmetry breaking states, but they break different sort of symmetries. So according to Landau theory, there cannot be a critical point, at least generic critical point separating these two phases. So either first order transition or coexistence of these two orders, according to Landau theory. But actual phase diagram, these two phases are separated by just a second order or Tomara-Lattinger-Rigid type critical points. So in that sense, the transition between these two is an example of so-called deconfined quantum criticality. Yeah. Although this transition had been known for a long time before this Centil Fisher proposal of deconfined quantum criticality. But I think they did mention in their paper that in 1D, because of the quantum fluctuation, this second order transition is certainly possible and that is known, but then they propose that similar kind of critical point can exist between these two. That's
beyond one. Doesn't that goes to like a Néel space or like that concept of 2A? That will be like ground state.
You mean J2? Yeah. If J2 is very large, then I think it's more like a coupled chains. Yeah. Because even sides are coupled by J2 and the odd sides are coupled by J2. Those become strong, and the J1 is just connecting between these two. So if you drive J2 to infinity, I don't remember exactly, but perhaps it again enters some gapless phase. which is basically like a decoupled spin 1/2 chain. But that's
only at A2 equal to infinity.
Yeah, maybe, yeah, okay.
A1 is a relevant perturbation always.
That's relevant perturbation?
Always.
Okay, yeah, maybe, yeah. But that's, yeah, another non-trivial question, yes.
This transition that Richard was pointing out between the dimer and the snail phase in 1 minute. So that the critical Tomonaga-Lattice equation that's fine-tuned with that is the parameter of R. So there is always a
Yeah. Oh no. You mean this transition?
No.
Between these two? Then you need to introduce the delta, so that breaks issue too. So the Lattice parameter depends on this value of delta.
But it's fine-tuned Lattice parameter.
Okay. Yeah, maybe I see your point. Okay. Maybe you're right. Well, I forward that. Maybe we can discuss later. Yeah. Okay. So, okay, I'm running out of time. But, so this is a constraint, but as I mentioned, this sort of you can derive. Of course, there are some very non-trivial assumptions, like when some perturbation is relevant, that potential term grows to infinity. That's very non-trivial assumption. But with some assumption, we can make some very general statement, and then we can physically expect that these conclusions don't really have to depend on this Tomonaga-Lattice framework. So it's probably more general, and physically or intuitively, you can also expect that similar constraints should hold even in higher dimension, because this number of particles per side is basic quantity, and it should also play a role in higher dimension. That's expectation you can make, and actually you can sort of prove that expectation. And so this kind of natural expectation we can make, and this has been actually proved in several ways, and those are what are now, well, generally called Lieb-Schultz-Mattistheorem or generalized Lieb-Schultz-Mattistheorem. Which is often abbreviated as LSM theorem. So yeah, let me just sketch the one version of the proof for higher dimensions. And I put quotation mark because what I'm going to say is not real proof in mathematics sense. Still kind of conjecture, but you can make some argument. And then there are more rigorous proof for the same argument. But yeah, I think what I'm going to discuss is sort of more easily understandable. That's my. So it works in higher dimension, in principle 3, 4 dimension, but let me sketch for 2 dimension. And it doesn't have to be square lattice, just any periodic lattice, but for simplicity, let me discuss square lattice. And you can consider particle living on each side and then hop to nearest neighbor, let's say, and they interact via on-site Coulomb or maybe next nearest term. So the Hamiltonian would look like T, jk, psi daga j, psi k, plus vjk, nj, nk, plus. And of course, I want to require translation symmetry in x and y direction. Then I assume so again, I impose U1 symmetry that corresponds to the conservation of the number of particles and also translation symmetry. Then I consider the finite size system of size Lx times Ly. Oh, and maybe before that, I want to fix the filling factor nu to be P over Q. And then I want to fix nu and gradually consider bigger and bigger systems. And but still, for each system is finite size of Lx times Ly. System size. And I want to eventually consider Samodite limit, but first we need to consider finite size system size. And then at this point, there is already some kinematical constraint of some sort, That is, the number of sites is Lx times Ly. And then filling fraction P over Q means that the total number of particles must be nu times Lx times Ly is P Lx Ly over Q. And here, I assume P and Q are coprimes, so you cannot divide by the common denominator. But total number of particles must be integer, otherwise it doesn't make sense. So this means that either Lx or Ly must contain the factor of Q, or the product of Lx and Ly must be divisible by Q. So there is some choice you can make, but here, for data convenience, I choose Lx to be some integer multiple of Q, and Lx is still integer or natural number. And then another constraint, this part is a bit artificial, but I choose Ly to be coprime with Q. That's one possible choice, and still within this constraint you can still make Lx and Ly very big, because eventually I'm interested in summary limit. Okay, then I want to put periodic boundary condition at least on the direction Lx, X, and you can also put periodic boundary condition in Y direction. So this is again kind of choice. Yeah, boundary condition in Y is not so essential, but for convenience. Then once you impose the boundary condition, periodic boundary condition, the system is like a torus. And yeah, you still impose the periodic boundary condition, but at least in X direction, it's like ring. So there is a hole inside. Of course, if you live on this system, square lattice, you don't see the hole, because this is just embedding into three-dimensional space. But intuitively, you can imagine you roll up this two-dimensional system to this cylinder, then there is a hole. Then in this setup, you can consider introducing magnetic flux. Phi inside this hole, and so of course, if you live on this two-dimensional system, you are not seeing this magnetic flux, but still there is the Haldane effect. So mathematically, you can forget about this picture, but still you need to introduce vector potential on this two-dimensional system to represent this flux. So this magnetic flux is equivalent to introducing uniform vector potential. In x direction, which is given by the flux divided by the system size, the length in x direction, Lx. And now, so these are, the first three are really the assumption for the statement I want to make. And the rest is kind of technical trick. But here I want to further assume that the system has a gap. Because the system can be gapless or gapped, but that's kind of trivial statement. So there are only two possibilities. So you have ground state, and if all the excited states are separated by gap, in which case we call the system gapped. And another possibility is that just above the ground state, there is a continuum of excited state, which is gapless. So you can classify any quantum many-body system to either gapped or gapless. And if the system is gapless, then I don't have any more to say. So let's assume the system is gapped. So at this point, I'm not losing anything, but I further assume that this gap is robust against this Aharonov-Bohm flux. By robust, I mean does not closed. So this is highly non-trivial assumption. So mainly because of this part, this is not real proof. I'm making some convenient assumption, but physically it's kind of reasonable because basically the effect of magnetic flux is represented by vector potential only of order of 1 over Lx. And also you can actually choose different gauge and concentrate vector potential at any link. So you can expect that the physical property doesn't depend much on the flux, maybe of order of 1 over Lx or something. And to some extent, you can prove that the physical property of the system does not depend on the flux. But as far as I know, there is not yet really real proof of this assumption. So I just need this assumption here. Then see what follows from this assumption. So now I consider starting from phi equals 0, and you are in the ground state, and then increase this flux adiabatically. Take a ground state. And because I assume the translation symmetry, translation invariance, this must be also, so ground state is of course the eigenstate of the Hamiltonian, but because of the translation symmetry, this ground state must be, or if they are degenerate, I can pick a ground state which is eigenstate of the translation operator, which is also eigenstate of translation. So Tx psi 0. So this Tx a lattice translation in x direction, and then this must be eigenstate. And so because this is unitary, the eigenvalue must be have absolute value 1 in general complex number. So I put this complex number as exponential of IP0. So this is a property of the ground state we can assume. And this P0 has a meaning of total momentum of the ground state. Then total momentum. Then starting from this ground state as an initial state, I increase this magnetic flux adiabatically. Zero to 2 pi. And this 2 pi corresponds to so-called magnetic flux quantum. And in some unit, this is hc over E, speed of light and Planck constant electric charge, if they have a charge. But in the unit, h pi equals 1, E equals 1, C equals 1, it's just 2 pi. And when phi equals to 2 pi has a special meaning, that's because, okay, so as I said, particles moving around on this two-dimensional system, square lattice, don't touch this magnetic flux directly because this magnetic flux is confined inside this ring or hole. So in classical mechanics, the particles are not at all affected by this magnetic flux because they don't touch. So classically, the charged particles can feel magnetic field via Lorentz force, but they don't feel directly the magnetic field. So there should be no effect. But in quantum mechanics, this flux confined inside the ring can still affect the motion of the particles on this two-dimensional system, and that's nothing but the Aharonov-Bohm effect. And this flux phi gives a phase difference between particle traveling this way or this way. Or in other words, if particles goes around this system, encloses this flux, then you pick up extra phase factor. That's nothing but phi. So this is the Aharonov phase. So for any generic value of phi, this magnetic flux causes Aharonov-Bohm effect. So it has some effect on motion of particle. But when flux reaches this unit flux quantum or 2 pi in the current dimensionless unit, the Aharonov-Bohm phase becomes 2 pi, and the phase 2 pi is nothing. So exactly at this value, the effect of magnetic flux should disappear, and the system must be equivalent to the original system. So phi equals 2 pi equivalent to phi equals 0. So, but this equivalence is not so obvious because the Hamiltonian with flux 2π. So this guy has non-zero vector potential because vector potential is introduced like this. So this is not equal to Hamiltonian at zero flux. So they don't seem like equivalent, but we can see the equivalence. The exact statement is that they are different, but they are related by gauge transformation. This is one particular type of gauge transformation which is called large gauge. And yeah, gauge transformation is the local change of the phase of the wave function. But phi equals to 2π means that if the particle travels around this system enclosing the flux, you get the phase of 2π. That means that in order to undo this effect, the phase transformation should be also topologically non-trivial. So you change the phase of the quantum wave function locally, but this phase change depends on the location, and when you go around the system, this phase change must evolve from 0 to 2π. But we can actually explicitly write down such operator easily. So Ux can be written as exponential 2πi over Lx. Okay, well, maybe I should say sum over lattice point on square lattice and x times nr, where r is xy and x and y are coordinate on the lattice, which are integers. So here I assume it's just a square lattice. Then you can represent coordinate by two integers, and x equals to 1 to Lx, and y runs from 1 to Ly. And if you do this, then basically exponential of I times some phase times nr number operator. So this is a number of particle operator. Then it changes the phase of the wave function according to this phase factor. And now phase factor is 2π times x coordinate divided by Lx, which means that this phase twist is originally near the origin it was 0, and the phase twist gradually increases over the system. And when you go around the system, x reaches Lx, then phase twist becomes 2π. So this actually exactly cancels this phi equals to 2π. So using this operator, this holds as identity. Then, so now we define the adiabatic flux insertion process. Then we can ask, so we started from the ground state, then adiabatic insertion of flux. And here I say adiabatic because assume that the gap doesn't close, then you can define adiabatic transition. If this assumption fails, gap closes, then this adiabatic evolution is not very defined, but if gap is preserved, then we can discuss this adiabatic evolution of this original ground state, which goes to some state, which I don't know exactly, but there must be some state. And then now I want to ask, what is the eigenvalue of this final state with respect to the translation operator? And actually the answer is pretty simple. So during the evolution, or this adiabatic insertion process, the Hamiltonian with any flux, it can be represented by some uniform vector potential, which is always translation invariant. So this always commutes with Tx. So that automatically implies that even though this state evolves, you do not change the eigenvalue of Tx. So, I assume that the original ground state is eigenstate of this Tx with this eigenvalue. Then the final state, or any state during this adiabatic process, should belong to the same eigenstate. Then intuitively, this sounds strange because this represents a crystal momentum. So this implies that you insert a magnetic flux, which actually induces electric field. But even under the electric field application, the total momentum doesn't change, which sounds strange. But the actual answer is that this is exact statement, but you cannot directly compare this eigenvalue with the original eigenvalue, because now we came back to the original equivalent situation, but you are in the different gauge. So after the adiabatic evolution, Hamiltonian is like this. So this is different from original Hamiltonian, although physically equivalent. The reason is that you are in different gauge. So in order to compare the total momentum or eigenstate of Tx in the original ground state and this final state, you need to go to the same gauge. So, but we are in different gauge compared to H of 5. So in order to make a meaningful comparison, you need to do large gauge transformation to get back to the original gauge. Then to compare with original initial states, we need to do large gauge transformation. So what should be compared is Ux times psi 0 prime. Maybe Ux inverse, but it's not clear. Then I want to know the eigenvalue of this state with respect to Tx. So maybe inverse is better. Anyway, So Tx times Ux psi 0 prime is given by Ux inverse times Ux times Ux inverse Tx Ux times psi 0. But actually, we can find out this easily because this is almost Ux inverse times Ux, which is almost 1. But in between, you insert a translation operator. So you change the indices of operators by 1. So as a result, this Ux and Ux inverse doesn't completely cancel because of the shift of the sites. But they still almost cancel. So Ux inverse Tx Ux is exponential minus 2 pi I by Lx. So, okay, so the effect of translation remains even after applying this Ux and Ux inverse because this is the only operator which can actually move the sites. And so rest of the operators seems to almost cancel, but they don't quite because this Tx changes this x to x plus 1. So this x plus 1 doesn't completely cancel with this, but if you can almost cancel, and the remaining contribution comes from shifting x to x plus 1. So plus 1 term doesn't cancel with this guy. So you are left with some extra factor, exponential of Lx 2 pi over I over Lx times 1 times NR. And this one comes from shifting x to x plus 1. So this still looks like non-trivial, but now this summation is 1 times particle number, and you add sum over all the particle number operator. So this NR is operator which can fluctuate, but if you sum over entire system, then this is nothing but the total number of particles, and which can be written using the filling factor nu as nu times Lx times Ly. So that means that so you get the extra factor exponential, and this Lx cancels with this Lx. So e to 2 pi I times nu times Ly. So Ly was arbitrary, so if nu is P over Q and Ly was multiple of Q, then this phase factor becomes trivial, but I can choose Ly which is co-prime with Q, then this is non-trivial factor. I want to make this choice, then what can be said is that this new state, final state, which must be also ground state because the gap doesn't close, has an eigenvalue of Tx, which is modified by this factor. Has a different eigenvalue of Tx with respect to psi 0. And I assume that the gap doesn't close, so this must be also ground state of the original Hamiltonian, and this was a ground state, the starting the initial state, and both must be ground state of the original Hamiltonian. So what can be said from this is that I started from the assumption that the system is gapped, then inevitably under these kind of assumptions, we have a degenerate ground state because they must be different. So from this ground state degeneracy. So basically, the statement is that if you start from non-integer filling factor nu, then if you have a gap, then you must have ground state degeneracy. So that is basically the same statement I derived using Tomonaga-Lattice theory, but this is more general. Doesn't depend on Tomonaga-Lattice and not even restricted to one dimension. Although in this argument there is some subtlety about this choosing Ly to be co-prime with Q and so on. But now there are more rigorous proofs. So okay, so I'm run out of the time, but up to this point probably many people already know, so I'm a bit feeling embarrassed. So I want to close by telling you some curious history related to, so this is one version of generalized Lieb-Schultz-Mattistheorem, but can I switch to the slide using the same file? Okay, yeah. So okay, so I explained that this Haldane conjecture about the difference between integer spin chain and half-odd integer spin chain could be understood as consequence of different filling factor, integer or non-integer. And I also explained that in more general framework that is related to the generalized version of Lieb-Schultz-Mattistheorem, there are a lot of generalizations, but in the history of Haldane gap business, this Lieb-Schultz-Mattistheorem theorem also played an important role, because as I said, initially people didn't believe, most people didn't believe, but gradually there have been several supporting evidence for Haldane gap. And one important supporting evidence was by Affleck and Lieb, a paper in '86. So after Haldane's conjecture, and they published a paper saying proof of part of Haldane's conjecture on spin chains. So basically here, they generalized the original Lieb-Schultz-Mattistheorem theorem to general values of spin quantum number. And they found that when S is half-odd integer, then the ground state must be gapless, or you must have twofold ground state degeneracy. That was their statement. And they say proof of part of, because this only applies for half-odd integer spin case, spin 1/2, 3/2, for which people already knew that the spin 1/2 chain was gapless. So the main question, at least for condensed matter physics people, was whether integer spin chain can be gapped. That for many people hard to accept. And this was not proof for that part, but still kind of suggesting, because this theorem only works for half odd integer spin. And as I said, this was just technically a generalization of original Lieb-Schultz-Mattistheorem theorem. And the original Lieb-Schultz-Mattistheorem theorem was published in this paper, actually Annals of Physics back in 61, so pretty old. And but I'm not sure. Okay, many people know this Lieb-Schultz-Mattis, but perhaps not many people actually went back to this paper. So I want to show how this famous theorem is discussed in this paper. So if you look up this paper, then you do find, but actually this paper, the title is nothing about the theorem, okay? Two solvable models of anti-fermionic chain. And actually the first example of solvable model is XY chain. So you can map to free fermion by Jordan-Wigner transformation, blah, blah, blah. Now kind of common sense in the field. But I think this paper is the first to do this explicitly. So it's a historical paper. So main result of this famous LSM paper is that this XY chain is solvable and you can calculate a lot of things. That's the main content. So what about theorem? And actually you can find this theorem, but only in Appendix B. So apparently they didn't think this result as so important. And if you actually look into this Appendix B, you can also find an interesting statement. So, okay, the proof, actually 1D version of proof was different, but I'm not going into that. But they proved this only for spin 1/2. So that's why many years later, Affleck and Lieb came and presented generalization to general values of spin quantum number. That's kind of well known in the field. But actually, if you look up this original Lieb-Schultz-Mattis paper, there is a curious remark. A further generalization to particles of spin not equal to 1/2 has been submitted for publication in the Journal of Mathematical Physics by Lieb and Mattis. Okay, so, but I tried to find this paper, and apparently this is a paper which is announced in this appendix here. But if you actually look up this paper, there's no mention about this generalization. Actually, there they announced two things. One is a further generalization of this theorem to spin not equals to 1/2, and also discussion of the ordering of excited state energy levels. And this ordering stuff is published here. So the announcement is fulfilled, but this part is not discussed in this paper at all, and I don't find any other paper. So yeah, so I don't know what, but I can make a guess. That is first Lieb-Schultz-Mattis back in 61, at least try to generalize because they, wrote they are going to write up generalization. So I think they tried, and maybe initially they thought, okay, this works for any value of S. But then at some point, perhaps they realized that, oh, this proof doesn't work for half-odd integer spin. So maybe they kind of discarded, okay, this doesn't work, so why bother publishing? So that's probably why, okay, perhaps why it hasn't been known for a long time. And only 25 years later, in 86, only after Haldane's conjecture, this Affleck-Lieb paper came out. But in principle, if Lieb-Schultz-Mattis tried to generalize and they published it, even though the proof doesn't work in half-odd integer spin chain case, then maybe this difference could have been known before for them, but the actual history didn't work out that way. So yeah, so maybe there was a missing evidence already back in 61, but kind of discarded. Yeah. So it's kind of interesting that this small result for spin 1/2 chain, which apparently the authors themselves didn't think very important, buried in appendix, and generalization kind of, they tried, but somehow didn't bother published, became so important, and can be a physical background of Haldane gap and many other problems, and now generalized to higher dimensions and in the presence of many other different crystal symmetries. So now this Lieb-Schultz-Mattistheorem and generalization is kind of one of the central concepts in quantum many-body problem. But at the beginning, it was kind of very humble. So maybe the moral of the story is that even if your result looks trivial, almost trivial or stupid, maybe you should write up and publish, and at some point maybe it becomes important. Maybe. Okay. Thank you very much.